The core objective of control engineering is precision. It is the ability to force a physical system's actual output to match a strictly desired target. The most basic approach to achieving this target is an open-loop design. This relies on a linear progression. A specific input travels through a system to generate an output. This architecture relies on a critical assumption. The machine operates in a mathematical vacuum, isolated from outside variables. Looking at this diagram, we see what happens when that assumption fails. Unpredictable disturbances collide with the system, forcing the output to veer off its target path. Because an open-loop design cannot detect or adapt to these interferences, the machine is blind to its own errors. It is unreliable in a physical environment. To engineer around unpredictability, the system must measure itself. By capturing the resulting output and routing it backward to the starting point, we give the machine a reference for reality. This structural redesign is defined as a closed-loop system. By returning the output data to the origin, the machine acquires state awareness. It transitions from a passive mechanical tool into a self-correcting system. This represents a calculated engineering trade-off. We sacrifice the manufacturing simplicity of a straight line to gain the reliable intelligence of a loop. To understand why open loops fail, we must examine the system block's anatomy. It holds two components, the controller and the process. The controller calculates the exact input required to reach a goal. The process receives this input, executes the physical mechanism, and generates output. We can observe this architecture in a standard immersion water heater. The physical components map directly to our diagram. The switch serves as the controller, the metal coil acts as the process, and water temperature is the output. The moment the switch is turned on, the system executes its single command. It has no mechanism to measure the actual temperature of the water, and it cannot track your desired temperature. Because it lacks state awareness, this open-loop architecture is guaranteed to fail its primary objective. It will continuously heat the water to a boil until a human physically unplugs it, or the device destroys itself. To fix this mechanical blindness, engineering dictates a requirement. The system continuously measures its own output. Looking back at our model, we capture the final output signal and pull that data backward, running it underneath the process and controller blocks. We then construct a summing junction at the front of the system. This is the error detection unit. The function of this unit is continuous comparison. It measures the arriving feedback signal, representing physical reality, against the initial reference signal, which represents the goal. The mathematical difference between reality and the goal yields a new value, defined as the error signal. This error signal feeds directly into the controller, dictating its next operation. If the output is too low, the controller increases the input. If it is too high, it reduces the input. By processing this loop, the system dynamically compensates for external disturbances, maintaining the desired output without human intervention. This closed-loop architecture governs the function of a standard room air conditioner. An internal thermostat acts as the feedback sensor. It monitors the ambient room temperature to combat disturbances such as body heat or sunlight. This graph tracks the system in action. When the thermostat detects a deviation, the error signal triggers the external compressor. By cycling the compressor on and off, the machine stabilizes the fluctuating temperature into a flat horizontal line. We can contrast our blind immersion heater with its closed-loop successor, the modern water geyser. The geyser accepts a precise thermal target as its initial input. Using its internal feedback, it adjusts its heating element to hold the water at that exact state indefinitely. The active integration of an error signal is what separates passive tools from autonomous systems. It is the dividing line between machines that simply run and machines that maintain. This matrix illustrates the practical compromises control engineers must negotiate between the two architectures. Open-loop systems lack a feedback loop and the associated hardware. Because their circuitry is simple, they are cost-effective and straightforward to manufacture. However, their inability to reject physical disturbances results in low accuracy and poor reliability over time. Closed-loop systems provide high accuracy, but they demand physical sensors and error detection circuitry. This drives up the cost and makes the design more difficult to build. Every deployed system represents a choice. The engineer must decide if the requirement for accuracy justifies the burden of complexity. Constructing a logical block diagram is only the conceptual baseline for building a functional machine. To engineer these systems into reality, every block, every error signal, and every feedback loop must be quantified into mathematical models, known as transfer functions. Calculating these feedback loops relies on a specific mathematical framework, the Laplace transform. Mastering the closed-loop architecture allows engineers to take an unpredictable physical reality and translate it into solvable, rigorous mathematics.